Hello and welcome to the never-ending search for enlightenment with me, Will Williams, your spiritual guide. Actually, I've got you under false pretenses. We're going to talk about hydrology. First of all, the drainage basin hydrology, the fate of water as it falls into the area within an interfluve or watershed if you're still working in babyland. Then the outcome, how that is measured, the hydrograph, the change in discharge of the major stream that comes out of a drainage basin, and finally, well, what is it within the drainage basin that's going to affect the outcome? So these three things are linked together, and this is the basis of everything from talking about flooding through to questions you may get on the semantics. Here's a lovely, beautiful hydrological cycle. Look, there are clouds at the top and there's fluffy trees down here. We're not really interested in that. Here's another example of the genre, and here you can see you've got the Windows, probably Windows 3.1 graphic in this. Notice we're beginning to get arrows. We're beginning to get towards the idea of systems analysis. Systems analysis uses blocks and squares for stores and arrows for transfers. Doesn't quite work with what I've done here, but we'll see how it goes. So precipitation falls onto the backs of sheep and vegetation, and that's interception store. Some of it, of course, falls straight onto the surface and falls to surface storage, otherwise known to you and me as puddles. And some of it is DCP, direct channel precipitation, and that falls directly onto the blue line network. That's all the tributaries within the drainage basin, within the interfluve, that eventually flow into the major channel. So the River Severn, for example, is a blue line network whose tentacles spread up into the Welsh mountains, the Cambrian mountains. That DCP, of course, is not that significant in size, and therefore we often ignore it completely. But if you want those extra marks, it might be worth remembering it. Okay, so water moves vertically downwards onto the ground, the soil moisture into the ground, the soil moisture store. And of course, if it's done that, it's passed through the ground surface, and that water which is infiltrated may percolate down through the groundwater, into the groundwater store. Difference between soil moisture store and groundwater store: groundwater is saturated, that means all of the pore spaces are full. Soil moisture store, you've got some voids with air in them, which is pretty good if you've got a respiring plant, for example. Okay, transfer processes. Through the interception store to the surface, we can have stem flow when it runs down the stem, there you go, or drip, otherwise known as leaf drip, and you can get through fall, although technically that means it's not touched anything. So through fall is just water falling to the surface without touching anything. So I don't go a bunch on through fall myself. Surface infiltration into the soil moisture, and then, as I say, percolation down into the groundwater. Have a look at the arrow from the groundwater going lower. That's because some groundwater actually seeps deeper and deeper and never gets into the channel, but we kind of don't talk about that much. Shh. The most interest to us, though, when we're talking about flooding and the response of a drainage basin are the horizontal transfer processes. There's the surface process, of course, of overland flow or runoff. Two types of overland flow: Hortonian overland flow, where the rate of precipitation exceeds the rate of infiltration. That means the water can't get into the ground and will move down the slope as overland flow. And then you've got saturated excess. That's when the ground is so wet that in fact there cannot be any more infiltration. The water has to move as runoff. That water which moves in the unsaturated zone is known as through flow, and that water which moves through the saturated zone is known as groundwater flow. And the groundwater flow contributes something called base flow in our river, and that's the water that keeps a river flowing even when there's been a long period of no rainfall. It's being fed by the groundwater flow. Obviously, runoff is the fastest route to get into your channel. Through flow and groundwater flow, the slowest routes. There is, of course, and I'll just move my noggin out of the way here, there is, of course, an upward movement driven by warm air and the sunshine, evapotranspiration, and that will come off the surface of the plants and animals, interception store. It'll come off the surface of the ground, off your puddles, and evaporate, and it will in fact come out of the upper areas of the soil moisture. To replace it, because of the very small pore spaces, water rises up, and it rises from the saturated zone into the soil moisture store if you've got small enough pore spaces. So sandy soils, for example, won't, but clay soils probably will. A nice loamy mix would be best. That's known as capillary rise. And of course, plants are taking things up in the process of root uptake, which also has capillary rise occurring as well. So that's it. Learn it, know it, reproduce it. You should be able to. There's a different version, and the only interesting thing here to notice on the right-hand side, where we've got the idea of the output of the system, and that is the discharge in the main river channel. That, of course, is measured by using a weir, and we'll look at what happens with that by reference to the hydrograph, which is a whole question in itself, but I thought I'd put them all together, and here we go. So here is your, oops, what's that for? Well, of course, your hydrograph will occasionally give us a trigger and remind us that floods can occur. Two types of response on hydrographs: they are flashy and prolonged. Flashy ones prolonged ones. Here's a hydrograph. Isn't she beautiful? We have key things to be able to talk about. Lag time, the difference between peak precipitation and peak discharge. We have the ascending limb, or the rising limb if you're watching in Windows 3.1, or what I call GCSE mode. And you've got the descending limb or falling limb if, again, you can't deal with too many syllables. And note on this one, we've got the base flow rising slowly. Remember, base flow is the water contributed by groundwater flow that keeps the river going in, quote, normal conditions. Good hydrographs should have an inbuilt, embedded precipitation graph, which shows you as a bar chart the sequence of precipitation over the storm event. It has the same time scale, but its own millimeters of precipitation axis. Sometimes you'll see it up here, pendulating downwards. All these hydrographs have got the same features. So if we look at the hydrograph, and there's one down the bottom here, the hydrograph is a composite, in fact, of the 3 different horizontal transfers. Initially, we have the fastest response, that's the overland flow component, which gives you the very quick response because the water moves rapidly over the ground, doesn't have to get through the pore spaces. Through flow, water able to move faster, but slower, of course, because it's had to infiltrate and then percolate. And then groundwater much, much slower. I use the term interflow here because in some jargon, in some textbooks, they call groundwater flow interflow. Correctly speaking, it should be groundwater flow. In fact, interflow is a part of through flow. So move on, keep it, and call it groundwater flow. Here is, in fact, from the AQA, 2 contrasting hydrographs. You've got the prolonged one over here, which of course in something like February might be a problem in Britain because we've had rain all the way through up to Christmas, which means your water table has risen and your groundwater is up to the surface, which means the water can't infiltrate, which means it's going to move as overland flow. If you then dump a big storm on top, you're going to get this one, the flashy response going on top. Something I loved about this question, what the heck happens here? Well, almost instantly the discharge dropped down. It's almost like the 7 bore or wild pulse of water went through. So our drainage basin and the relationships of what's going on in our drainage basin will give an output as can be measured and described in our hydrograph. But what is it that determines what happens in our drainage basin? Well, these are the characteristics of the drainage basin. Number 1, the shape. Is it a circular drainage basin where every point is quite close to eventually getting into a channel and the blue line network and therefore going to give you more likely a flashy response? Or is it going to be a prolonged one where the furthest point away, it's going to take a long time for the water to get to that channel? River basin, relief of the basin. If it's very steep, for example, Bangladesh has got 2 major tributaries to the flooding area of the delta of Bangladesh, which flow off the Himalayas. They're quite steep. Good old mg cos theta, that's the component of gravity acting on water down a slope, very, very high, meaning you're going to get quick runoff, probably going to get therefore very, very steepy response. Rock type, if you've got a granite, it's impermeable, water stays on the surface, it's going to move as overland flow or runoff, they're going to give you a steep response. Sedimentary rocks or rocks that have got high porosity, they will probably tend to give you more infiltration, and they may in fact give rise to better quality vegetation in the first place. So you may in fact have a slowing interception, slow for infiltration, and therefore you're going to get a more prolonged response of your drainage basin. Vegetation amount. How much of your umbrella of your canopy of vegetation have you got to intercept and slow down the response of the system to give you your hydrograph? Don't just think about vegetation amount, think about vegetation type. Some vegetation is equipped and adapted very quickly to get rid of water, so rubber plants, for example, with the drip tip leaves, you remember that. They're very good at moving water rapidly from interception store to surface store, but mainly if you've got a load of vegetation, you're going to get a slowing down, you're not going to get a flashy response. Antecedent conditions of what was happening before. If you had a long period of rainfall, then you're going to have a saturation in your system, and therefore you're likely to have a high base flow, remember this bit here, and you might find that any storm event is sitting on a very saturated environment, giving you a compound problem, as I talked about. Typically February, when you often see those people from Sky News standing outside pubs with people canoeing down the main street because, oh my word, it's flooded in Tewkesbury again. What else do we got? Humans, we have to mess things around. Urbanization, of course, we don't want water on our urban surfaces, or guttering, or drainage systems, all designed to accelerate runoff. Even if it's just below the ground, it's still really runoff because of the pace, and off it goes, and it'll give us a short lag time, steep ascending limb, steep recessional limb. Rural, often missed by a lot of people. We do a lot in rural areas that can exacerbate the flood hazard. For example, we can deliberately drain the fields. If we drain fields, we're accelerating through flow to make it almost comparable with overland flow. Come on to that in a moment. We also have soil characteristics. You may have a soil which has got a pan within it, an iron pan, and that means even though below the iron pan the soil may not be saturated, water cannot percolate, and therefore you're going to favour your runoff and through flow, giving you a slightly peaky kind of hydrograph. And finally, the nature of the precipitation event. Is it a really intense summer storm? And is that falling, for example, antecedent conditions? If it's been very dry in the summer, you've got a calcretion on your surface layer, if you get a very heavy storm, then we might get Hortonian overland flow. That's the condition where you get very, very rapid, intense precipitation. It doesn't infiltrate, and therefore it has to move as overland flow. And that causes a flood, flash flood hazard. And those of you who've done arid environments, you'll know that this is what happens when you've got a duricrust and then you get an intense cloudburst. You're going to get quite a lot of surface fluvial erosion, which of course doesn't make sense to many people who think deserts have got no water. Okay, A plus B equals C. Whatever's going on in the characteristics of our drainage basin will affect the drainage basin or the engine to produce a result, C. A, the characteristics, B, the drainage basin responses, C, the outcome. You may get questions that ask you about C, for which you might need to think about the B and the A. You may, for example, have questions about B that make you want to predict what will happen with C. Just remember the sequence. Whatever happens in C is a result of A plus B. I think that's enough Sesame Street algebra for now. Here you pause me, get rid of me, and look, I'll put myself somewhere out of the way. You might want to look at each of the factors. I've ripped this from a geo something, and they pretty much summarize all of them as they go through the impact and the reasoning. I've been through quite a lot of these points. Antecedent conditions I've put in there, and you'll find when you get a bit further on, you'll get to what happens with rural land use, because it's not really covered very well in the textbooks. So tile drainage, farmers deliberately embed gutters in the upper surface but below the ploughing depth of their fields, and these gutters have got an earthenware tile on top so water can percolate through that tile but then goes into the gutter and runs off down with gravity off into a ditch at the end of the field, where it then goes and joins the blue line network. So that kind of accelerates through flow. So you're accelerating the fast responses over than percolation, groundwater flow, etc. Crop type. If you imagine yourself as a bird, close your eyes, bit of enlightenment, and you're flying over a field of wheat, you're seeing dots and a load of surface. That's very different from if you flew over an orchard where you'd see a large canopy of fruit-bearing trees. That's clearly a different level of interception compared to the crop type. Again, add a nuance to your answers and don't just say vegetation. There's something more you can say. Bear in mind, all of these things change temporally as well. It's not just deciduous trees that drop their leaves. We get a variation in cropping and the impact that has on the local hydrology. Crop type, and finally the plough pan. Sometimes you put a massive Ferguson tractor over the land for too long and you don't deep plough, you compact the ground at a certain layer in the soil, which gives you, if you like, an artificial impediment to percolation, again leading you to potentially having a faster response of your drainage basin because it favours through flow, and then of course if that fills up it's going to favour runoff than you might imagine. Okay, it's not a benign environment. So there you go, A plus B equals C. The hydrology of a drainage basin. You will probably be asked about it to do with flooding. You may be asked about it in isolation. Pause, have a look at the video, go back, listen to my words, copy down some of those things, and all I can say is good luck.